The graph isomorphism is important because in reality you have a lot of graph, a million of graph defined on the same set of vertices and also on the same set of edges, but they are sorted or structured in different way uh, using some mapping. Okay, so that's why we start by looking to this symbol definition here, where you have only two graph G and H. The first graph G defined on vertex V and H set E. The second graph capital H to have the vertex here W and the H set capital F. Okay, we say that G and H are isomorphic, and you see the one here isomorphic different from the one we learned in planar graph. We have homeomorphic. Homeo mean the same, iso mean equal under some bijection. When you learn about the function theory, you have the injection, surjection, and bijection. So bijection means iso. Okay. So the graph G and S are isomorphic. This is Vietnamese. If first of all we can find out bijection from the vertex set V of G to the vertex set W of H. Okay, the second graph. So V from G and W from H, the bijection from one graph to another graph. Not only that, the bijection F here, however, must maintain or must reserve the adjacency relation as well. So you can define any bijection between two sets with the same number of elements, but the second condition here is special. Okay, the bijection from V to W maintain the adjacency relation. That means if you observe some connection in the first graph G, so this is the H, we write small t, moving or connect not U with not V in the first graph, then you can find out the image of U denoted by Fu in the second graph here, and also you can find out the image of V denoted by Fv here in the second graph, and the two nodes in the new graph here also must connect together to make a new connection. Okay, you see F here. F here means the set of connection in the second graph. So the requirement is here, equivalent. So that means whenever some connection in the first graph, then after finding the images in the second graph, the nodes still connect together. Okay, so we can interpret that in this sentence. If U and V are adjacent, that means connect together in capital G. If and only if, yes, this one, if and only if, equivalent to say that the image is also adjacent in the second graph. That would be true for any choice C, U, and V in capital V. So isomorphic require two conditions. Exist some bijection between the two vertices, that is the first. Secondly, the bijection must maintain the adjacency in this sense. Okay, then if the two conditions are satisfied, then we can have an isomorphism. This is the technical term. Isomorphism is a noun, isomorphic is an adjective. Okay, So isomorphism here can be written, in the full sentence like this one. So G and H is isomorphic together if you can find out one-to-one correspondent. One-to-one correspondent mean bijection between the vertices of the two graphs, and then that one reserve the adjacency relationship. So we can see that one in this example. This one is the first example. Okay. We consider the first graph here on the left hand side having only 4 nodes, U1 up to U4. And you can look here, let's say U1, U2 connect together to get this connection E, see? And the second graph I write on the right hand side, you see? So we can define some bijection. So that bijection F give the image of U1 to be V1. So I write here U1 going to V1. So U1 is here. So V1 is there. Understand me? So this one become the image of U1. Understand? And how about V2 here? You see V2? And V2 here divided to be the image of U4. So you see the image of the last node in the first graph. Because the bijection, then that means the mapping F give 4 nodes in the left to the 4 nodes in the right, you see. And how about the image of U2? We define here. Okay, image of U2 equal to V4. So this is V4 right here. So V4 here become the image of U2. So I write in the final line of the string. Okay. I keep that for you here. And you see, if you look to the graph G, U1, U2 connected, and their image become V1 and V4 in the second graph. Okay. And they still connected. You see? So that means the condition we explain in the definition here are fulfilled. Understand? So I can denote the connection U1, U2 here by T to maintain the definition. Okay? U1, U2 here is T. And after you get the connection, you get the new node in the graph H to be V1, V4, and you get this one us if we employ the relation there. Okay? So that's true for any choice. So if you have U1, U3 connected together and you see U1, U3 here, and the new node will be like this one. And you have to check this one, V1, V3, V1, V3. Yes, they still connect in the new graph. Okay. So basically the mapping F here fulfill the second condition. So therefore this one eligible to call isomorphism between the two graphs. So this is a perfect example for the concept isomorphism. We choose small graph and we either set that and we prove that. Okay. Why we study graph isomorphism? You may ask a question. Why the isomorphism is important? The reason here is that if the two graphs are isomorphism, then we can store in computer once. We don't need to store both graphs. We need to store only one graph. So Okay, and factorial mean how much are they? Factorial guys, the value. Well, it should be like 5 multiplied with 6. You know that, okay? And you ask me the n factorial of 5. So 5 factorial, and you don't know. And you have to require property of factorial. You say, okay, for factorial multiply with 5. Now might be easier because you know 4 factorial turn out to be like this, and you know the value like that. You see? Then you know 6 factorial, which is 700 something. Okay, 6 factorial about 700 something. Maybe 720. Please check that for me. Okay. So the total number of bijection is very huge if you go with large, you know, graph. So therefore, a lot of connection. Trying connect lost connection. Hello there, you hear me? Okay, good. Get back here. So we move on with this one. After realizing that testing two graphs to be isomorphic is not easy. Okay. So take a look here. How many nodes are there in the graph here? Number 5. And the right hand side also number 5. Okay. Then the one here isomorphic or not? How can we check that? You have to show the mapping with the bijection. So by definition, you have to go through every step. You have U1, U2, U3, and you have to define the map going to from the first draft to the second draft, like this one, and you have to define U1, U2 connect. Then you have to write here image here V1, V2 connect. You see, etc. So you have to check through all 5 tutorial, which is not easy. How about the second one here? We can confirm the first one is okay, yeah, because here you have kind of, a path going through a change of node, and you can do here 1, 2, 3, 4. You can draw that way, and here you have also 4. So easy to check by hand. But how about the second one here? We don't know yet. Okay, we don't know yet. But somehow, if you look to here and you see that the degree of the node here may be not the same, okay, or are they the same, etc. So to check non-isomorphic sometimes easier, okay, because if there are some certain property of the graph she fulfill, but with that property the second graph does not fulfill, then we say that the two graphs are not isomorphism. I mean, in terms of formalization of isomorphism, if the two graphs are isomorphic together, then the property of the two must be the same. Therefore, if we discover some property, some particular property, which is not the same, then we say the two graphs are not isomorphism. Okay. So if I count here, I say 4 degrees here, and here also 4 degrees. That's fine. And this is 4 as well, the second one. But if you look to the second graph, you see somehow only one node having degree 4, like this one. Meanwhile, in the first graph here, we say the second node B, and if we did not this one to be the next node C, and node C having degree 4 as well, you see. Meanwhile, on the right hand side, this one 3, this one 2, this one 4. Okay, so you can say, well, so far the degree of 2 node B and C to be number 4 here, and in the second graph you also see that. So we almost believe they are isomorphism. Okay, they are isomorphic together. So that trigger our next step to realize the property in the isomorphic graphs. And if we discover something not true for both graphs, then we conclude the graphs are not isomorphic. Okay. That property we call the invariant, graph invariant. And I show you another example about that, and you can check yourself. Okay. So this is G1 and this is G2. How many nodes here? 1, 2, 3, 4, 5, 6. So you have the number of nodes to be number 6. And here you have A, B, C, D, or F. So also 6. So that means the number of nodes are the same. You can define the mapping between the two graphs. And you have to check the adjacency again. And you have to go through the number of bijection like this, and everything very huge, etc., etc. That's why I confirmed before that to check isomorphism is not, symbol action to do. Okay, and well, let's see A, B, C, D here. The vertical node here, all of them having degree 2. Yes, degree 2. But if you look to the right hand side, you see somehow only this one has degree 2 and no more. You see? This one have degree 2. Okay? Only one node. The left hand side in the first graph, you have 1, 2, 3, 4 nodes. So that means the number of nodes having the same degree 2 are not the same. This one gives 4 nodes. This one gives only 1 node. Oh, you have here B. Also degree 2. Can you count more for the left hand, for the right hand side? No, only F and B. So I update the right hand side here having 2 nodes with degree 2. So I almost confirm that the two graphs cannot be, because by the property of if the adjacency relation is fulfilled, then the number of nodes having the same degree must be the same. Okay. So we formalize what we observe to the next concept. We formalize what we observe in the last example. You do this one yourself, I don't explain. The third example, we move on, and we move on. There are more examples to be the exercise at home, to be the homework for you, homework to do yourself at home, to read the definition of isomorphism, to understand that, and to learn from solving this one. In this exercise, this one is interesting because I don't draw the graph, but I give you the adjacency matrices. That means if you want to test, you have to draw the graph. Okay, so the graph G1 is the graph G2, and you test the isomorphism. Then maybe more, yes. So this is graph G1, G2, and draw again. And apply the method by using the matrix here to draw the graph and then to test the isomorphism. Homework. Okay? And then more than that, so there are 3, at least, a few exercise for you to play at home after lecture today. Now we don't have the adjacency matrix, but I give you the incident matrix. So again, this is G1 and this is G2, and the graph here, the matrix here are not adjacency. The matrix here are incident, and you have to employ the definition of incident to recover, recover the graph, because you remember the adjacency matrices and the incident matrices are among the three ways um, for describe the graph. So we employ the two of them to draw the graph before you check the isomorphism. Okay, having the graph you can check, but look into the matrix you are not able to do now. Okay, so this is G1 by adjacency, no, by incident, not adjacency, and you have to draw them. You have to write down explicitly information for G1, G2 before you can test the isomorphism. Okay. So another exercise to talk about the isomorphism. In any exam, at the end, we always have kind of question. Okay. Then we want to do more by extend the definition of isomorphism of symbol graph to undirected graph, but now allowing the groups and multiple axes. Multiple axes we call multi-graph, remember? And then we move on with define isomorphism for directed graphs. So you have to think the exercise finish at this line, and this one is the new motivation for the next slide. Okay, so this is the revised session, the review exercise for you. This one means adjacency matrix. Adjacency matrix. If you write adjacent, mean the property is the adjective, and this one means incident, right? The adjective for it will be incident. Okay. Incident. If you consider this one to be adjective, okay. So I give you G1 and G2 here. Well, the left hand side. So how can we think? Yeah, very interesting. This one very interesting exercise. Be careful, because the G1 here given by the adjacency matrix denoted by AG, but the G2 here given by incident matrix denoted by IG. You understand me? So that means we describe G1 different from G2. Okay, so we define G1 by adjacency matrix, but we describe G2 by incident. So we give two different matrices, but ask you to draw G1 and G2, because after that we ask you for a question here: are they isomorphic or they are not isomorphic? Okay. So you don't need to solve C and D because we not yet define that one. Yet try to do this one. Okay. Then we move on with the second revision here, where we provide the complete key file and then provide the complete playback time key 3.2. Then we ask you to choose which one is correct here. Okay, so isomorphic or not, the same number of vertices, the same number of edges, are they isomorphic? Well, if you say A is correct, then you cannot choose D, of course, all the way around. So that means not all of them are correct, only one or two of them are correct. You have to do this optional, choices. This is revision number 3. Now we talk about symbol trap undirected, and you have to choose the correct answer as well. Which one is correct here? So this is kind of revision for lecture number 8 about the trap theory. Okay? So you have to know what is the isolated vertex, about the degree of vertex, okay, and bendant vertex here, etc., etc. So have to be careful with that exercise. This is number 4. Well, you can read this one and do this for fun. Okay, revision number 4 in Vietnamese. I don't translate. Revision number 5. Is that one number 4 before? Yes, correct. This one is number 5. So in the number 5, we are given this trap, undirected trap, okay, and ask you to find the adjacency list, adjacency matrix, incident matrix. So there are 3 ways to represent the graph. So we review about that representation. Review about the representation of the graphs. Okay, and then we ask you this one bipartite or not, and then if you can, then you can draw on 2D or not. So the last one, we check your knowledge about the concept planar representation. Okay, so this is about revision 5. You have to do fast at home, not long. So if you do the exam by multiple choice form in the exam, then you have to solve this exercise. Maximum, I think, the time for solving this kind of exercise will be maximum about 5 minutes total, not longer, because you have a lot of questions in the final exam. Okay. Try to do fast and precise. Okay. So any other things? Yes. So this is revision number 7. This for fun. Do this yourself, DIY. So the exercise, the higher number means the more interesting you can do. And this is the last one where we talk about project with manager. We define to be A, B, C, D, F, G. So you can use the graph to model this project A, B, C, D, E, F, G. That means if we did not one job by one node, then the graph would have nodes. Okay, A, B, C, D, E, F, G, and the job can be done. We process and we provide the time to process the job A in 5 days, job B in 2 days, etc. And job G, imagine that by some like first one, job B like that in this case, A, C, D, G, because what to do then we know how the connection. So you don't know, make the SGs. We draw the trap. You see, so assumption to help you to apply abstractly. So this one means generally, in a general case, generally, okay, general. We have x1 up to Sn on the left hand side defined to be the job, and also you have m job on the right hand side, the y. The problem is we employ this very special notation. Yeah, I am trying to explain here. Yeah, I am help you to understand that one. Why? Don't worry. What the sim, right? What? This one, right? So this one is new to help you to draw the graph. We say s1 up to sn plus together smaller than or equal. So this one is not the equality between the